also very exciting. If Laura was here, I would have been probably happier, but I'm glad I could see her there. Thanks for organizing, Laura. So today I will be talking about when working memory reactivates information that is available in long-term memory. And this is a series of experiments that are run by our lab members, two of which are here today. So they have contributed greatly. Thanks in advance, Shashan and Sena. If you have any questions, please feel interrupting me, at any moment. You don't need to wait until the end of the talk. All right, let's get started. Working memory and long-term memory constantly exchange information in daily life. And let's give an example to understand that a bit better. Imagine you're preparing for a loved one's birthday and you come up with a gift idea. You hold it in working memory as you consider this idea. Once you have settled on it, the idea is transferred to long-term memory to retrieve it later when you need it. Later, when you visit the gift shop, you can retrieve this gift idea from long-term memory. Influential memory models suggest that whenever information from long-term memory is retrieved, it is reactivated in working memory. However, working memory is metabolically costly because it depends on extended, if not sustained, neural activity. And therefore, an energy-efficient memory system should minimize unnecessary reactivation of long-term memories in working memory. Reactivation instead should be specific to the conditions that need working memory. And if it doesn't need working memory as much, working memory reactivation should be bypassed and behavior should be guided directly by long-term memory. In other words, reactivation should be selective to conditions that require working memory. Where would this need for working memory reactivation come from? First, many memory models propose that working memory is more accessible than long-term memories. This would suggest that long-term memories might be reactivated in working memory primarily to guide behavior more effectively. Second, given the focus of attention within working memory is proposed to be robust against interference, reactivation could help protect information against interference, especially if there's only one item to remember that could be held in the focus of attention. And third, long-term memory might be less flexible for adaptation because it's stored via structural neural changes, while working memory relies on extended neural activity, which arguably is more suitable to be revised based on the current needs because it's more flexible as it's still an sustained activity as opposed to a structural change that takes place over long durations. So today I will present studies that test each of these possibilities. To evaluate whether memory reactivation supports behavioral guidance, we tested how anticipating attentional guidance influences memory reactivation. The experiment consisted of 3 phases. In phase 1, participants viewed a series of 24 real-life objects presented one at a time. Each object appeared 3 times in a randomized order. In phase 2, we verified that learning was successful. Participants were shown pairs of objects. You don't see my mouse, but you can see a pair here. And then participants had to select which one was previously studied. To proceed to the 3rd phase, they needed to respond correctly to each item that was tested at different times, 4 times without any mistakes. So we really ensured that these items were learned. Here, for example, the participant presses the up arrow, indicating that they have studied this white pen and not the blue one, and that's a correct response. Sorry, actually here it's an incorrect feedback, sorry. So they have chosen the bottom one, which is the blue one, and they're shown the correct option with the green rectangle. And here they're selecting the correct one, which is blue pouch. So they get this correct feedback. And every time they made a mistake, they restart again from scratch. So they need to do 4 correct responses starting from 0. Phase 3 was the main experiment where we measured reactivation in working memory using EEG. Each trial began with the presentation of a previously studied memory object along a non-target object on the opposite side of the screen. This setup of having 2 items, one on each side, was because we wanted to use a lateral EEG index of working memory, and we wanted to match the perceptual input to each hemisphere. In this case, the item was shown with the blue side of the circle, telling that participants needed to remember this item on the left and ignore the hat. After a retention interval, participants performed one of 2 tasks. In the recognition task, they indicated whether the probe matched the memory item. In this case, it's not a match, so the correct answer is different. And in the search task, they indicated whether the memory item appeared on the left or right side of the screen. In this case, the memory item, which is a white pen, is on the right side, so the correct answer is right. Thus, while both tasks required an accurate memory representation, the search task involved additional task demands. And we measured the working memory reactivation during the anticipatory period before these tasks. So here is the retention interval during which we record the CDA component, which I will describe in 2 slides. So comparing the 2 tasks, both required a memory representation, but the search task had additional demands of guiding attention based on that memory representation, while recognition only involved remembering the item and indicating if the probe matches it or not. Here are the reaction time results for both the studied items and the novel items. Oh, by the way, I didn't mention that not all items were studied. We also had novel items that were not studied that were shown in this 3rd phase. I'm constantly getting this, the speaker has changed to something and it will be used and whatever, which is a bit disruptive, so sorry for forgetting that. But here we had not only studied items, but also novel items. So for example, participants could also see some object they have never studied before. And that constitutes a baseline condition for us where people have to rely on working memory. They have no other choice because it's a completely new object. All right, so first, the behavioral results. Here you can find the reaction time findings. Accuracy was basically at the ceiling, so I'm not showing that. For reaction time, for both studied and novel items, the reaction time was higher in the search task compared to the recognition task. I'm not sure if you're familiar with Bayes factors, but basically larger than 10 means strong effect. And in this case, we have a strong effect for both. Search is slower than recognition, regardless of the item being studied. This indicates that the search task had greater demands on the participants. To assess working memory storage, we used the contralateral delay activity, and that's the measure for all the experiments, not just this one. So please try to understand well. If you have any questions, please don't hesitate to ask. It's a negativity on the contralateral hemisphere compared to the ipsilateral hemisphere relative to the memory item. So in this case, the memory item is on the left. Therefore, the right hemisphere is contralateral, where you have more negativity. In this case, negative is up. And then you have more positivity on the ipsilateral one. And importantly, this negativity is sustained during the retention interval in the absence of any stimulus, which means this is not about a perceptual imbalance, but rather due to memory demands. And this is why we had one item on each side. Even if the hat has no task relevance, we still put it there so that any lateralization doesn't appear because of a perceptual imbalance, but rather an imbalance between the 2 hemispheres due to a working memory demand. Here, participants needed to remember the item on the left while ignoring the item on the right. And in the absence of any physical stimulus, we continue seeing this lateralization, a sustained negativity on the contralateral sides at the posterior occipital channels. Yes, Tim.
Was in this memory array, was the were these objects always either already presented in this learning phase before, or would it also be that on the left side there was an old object and on the right side there was a new object?
The irrelevant side was always new objects that were not studied before, if I remember correctly. The memorized sides were studied in the studied condition, and they were completely novel in the novel condition. But for the other side, where we had non-targets, they were, I think, almost always novel. Maybe they were repeated once or twice throughout the whole experiment. Do you remember, Sana?
2 times, I guess, but it's like more than 1,000 trials, so they don't realize.
So we wanted them to be not previously studied so that they would have a better sense of ignoring them and knowing that they're completely task irrelevant. It's nice to have you here. Yeah.
How did they respond? Button press?
Yeah, so they did respond with button presses. Let me go back. For the recognition task, they had to indicate same or different. Was it S, D or something?
No, the same or different. Oh, this is
but for you it was different because you had 2 items. Yeah, so I'm not sure, but I think it was S or D for the recognition, and for it was left arrow and right arrow to indicate if the target was on the left side or the right side of the screen. So they had different pairs of keys. Yeah.
So what happens when they're in the novel condition? There were only novel items presented?
Yes, so
there was no CDA in this condition?
No, so the CDA, let me go back to the CDA slide. So the CDA is actually typically measured with novel items. We are one of the few labs that use previously studied items. And the idea here is that if compared to the level of the CDA when people store new items, which is the CDA is basically a measure of how many items you have in working memory. If you have smaller CDA, then it would imply that people are not relying on working memory to the full extent. This slide, I will describe the CDA, so it should hopefully be a little clearer. But if by the end of this slide, your question is still there, maybe then.
I think my question is, how do they know which one of the items is the target item?
Oh, yeah. So the blue side indicates for some subjects it's the blue side, for other subjects it's the yellow side that indicates
the color in the center.
Exactly. Yeah, that's it. Yeah, sorry, I didn't get the question. Yes, so the center cue. Sometimes we use a diamond or an arrow, but this is a bit more balanced in terms of being the same for each hemisphere. We have the same level of stimulation. So people have to just know which color is associated with the target.
So this could also mean for the studied condition that the target item was not the already studied one.
Was always new.
The non-target was always new. So here in this case, the blue shows the memory item. The memory item was either studied or not, depending on the block. So it was a blocked manipulation. But the other item that was to be ignored was always new. When I say new, it could be repeated only once within 1,000 trials. So almost. Yeah. Thank you. So the CDA is a widely used index of the number of items in working memory. Here on the y-axis, you have the CDA amplitude, and x-axis, you have the memory load. And as the memory load increases from 1 to 2, the CDA increases from about 0.7 to 1.2 or so. And then again, from 2 to 3, there's an increase up to about -2 microvolts. But then after 2 microvolts or so, well, actually, it's not about 2, but it's rather how many items. After 3 or 4 items, it reaches a plateau, so it does not increase anymore. And the capacity of visual working memory is about 3 and 4. So it really stops at the capacity and does not increase anymore. Moreover, where it reaches this plateau differs depending on that individual's working memory capacity. So if an individual has higher capacity, like 4 or 5, the plateau is reached at about 4 and 5. If the person has a capacity about 2, the plateau is reached about 2. So it really tracks the capacity of the individual, the amount of increase across memory modes. which shows that it's a reliable index of the number of items stored in working memory. What is also nice about it is that it is unaffected by anticipated task load. So if I tell you to store a pen for a recognition task, or an easy search task where you're searching for a white pen among blue other objects, or if it's a demanding search where you're searching for a white specific pen among other white pens. So really different demands have zero impact on the CDA because in each case, you're storing just one pen in your mind. It's really sensitive to the number, the quantity of items in your mind, and not about the general arousal level, anticipated difficulty of the task. So it's really specific to the stimulus, which is why it's suitable for our studies, because in all our studies, we change the anticipated task demands. We care about where people store it, and we don't care about the difficulty of the upcoming task. And also important for the purposes of today's talk is that if people repeatedly store the same item, so if I show you a pen and the next trial, again, the same pen and again, the same one, after 6 trials or so, the CDA mostly diminishes if you keep storing the same item, while performance is increasing. So we have less working memory storage index, but better performance. Therefore, it should be reflecting learning. I'm not relying on working memory, but I can still do the task. How? Probably because I rely on long-term memory. So it's a beautiful index for gauging the extent to which individuals rely on working memory to store information available in long-term memory. Now, if you're not familiar with the CDA, and if you have any questions, please ask it now, because I will talk about CDA throughout the whole presentation. So the more negative, the more working memory is the summary. All right. Now let's have a look at the CDA results. Here on the y-axis, I have the CDA, negative is up. I have studied a novel. And for novel, which is our baseline condition, where people had to rely on working memory because they didn't see these items before, we have a reliable CDA for both the search and the recognition tasks. And the level of CDA does not change between the two tasks, which makes sense because whatever you're going to do with it doesn't matter. You have to store it in working memory because it's a novel item. But if they were previously studied items, which means people can now rely on long-term memory if they can and want to do so, we have a different pattern. Now, for recognition task, we still have a reliable CDA, but for the search task, the CDA is smaller. So individuals rely less on working memory to store an object if they're going to use that object to guide their attention. Now, this is exactly opposite of what we predicted.
That was my idea.
So let's try to explain why that could be the case. We have 2 possible explanations that are kind of related to each other. The first explanation is that maybe guiding attention or doing the search is more efficient when it's done by long-term memories compared to working memories. And we do have a little bit of evidence in support of that in some of our previous work, where when the same target was repeated, that decline in the CDA that I showed you 2 slides ago predicted faster performance. So maybe for some reason, long-term memory is better in guiding our attention. The second and related explanation is that if I push my working memory representation to long-term memory to store the target, to do the search itself, I can have more working memory resources. So there's a trade-off between how much working memory resources I devote to storing the object and how much working memory resources I devote to do the search. If I don't devote as much to store the item because it's in long-term memory, it means I have more working memory resources to do the search. Arguably, that also requires some working memory demands because I need to process each object, put it in my mind, compare it with the target, decide if it is the same or not, move to the other one, right? So there's a little bit of storage and comparison demand, which arguably also requires working memory. So if I store the target in long-term memory, I have more space to do that. So maybe that is why people, when they anticipate a search task, they open up space in their mind by relying on long-term memory to store the target. Which is a post hoc explanation, I must admit, because we expected that search should have larger CDA because to guide attention, we need more accessible representations in working memory, but that was not the case. Yes.
Did you test to which extent the CDA effect is linked to the response time?
There was no relationship. Yeah, so I don't know if it's due to noisy measures and not having many people, or that my explanation is faulty, but
How are we to do it? Like median split or float or something?
I think we just correlated the average CDA, so on a subject level, average CDA and their reaction time on that condition. Probably we also tried trial level.
To do like fast versus slow trials per
Yeah.
individual and like per participant.
Yeah,
Based on the median of response times per participant.
yeah.
And then see whether fast trials maybe are associated with larger CDA.
I'm not sure if we did median split, but I'm
The other way. Yeah.
I'm almost sure we did a correlation between the CDA and the search in all trials.
Mhm.
And then we have correlation score per participant, and then we test if that correlation average is larger than 0. That I think also didn't work out. And we probably didn't try median split.
But there you have the problem that like single trial CDA is kind of strange, right?
Yeah, yeah.
You need more than one trial actually to measure it.
Yeah.
Okay. So
At least 120 or so to have a clean one. So I agree that it's super noisy. This is why, I mean, for us, getting correlations with behavior with EEG is always challenging. So if we don't have any correlation, I don't think it is strong evidence for the lack of a relationship. But I agree that we can try the median split.
what I meant was not the noisiness, but that like contralateral versus ipsilateral, the calculations just requires that. So what you then can do is like,
Oh, I
this
see.
is right.
No, so contra and ipsi comes from a single trial where, let's say if the item is on the left,
Yeah, exactly. But then it's not like, yeah.
then you have just left. Yeah, exactly. So when you subtract signal between two hemispheres, it's always noisier, and EEG is already noisy. So, I mean, yeah, it's a tough one. But yeah, median split is something we can try. I will definitely go for that one. All right. So these are the two possible explanations. So going back to the big picture, we had 3 reasons, possible potential reasons why people might require working memory more than long-term memory. And the first idea was to guide behavior or interact with the world, in other words, because working memory is suggested to be more accessible. So if I'm going to find something in the world, I better keep it in the focus of my mind to do that. But our results show that not really. That's, if anything, to better interact with the world, to preserve my working memory resources, maybe it's better to put that idea to the bottom. So the first idea to guide behavior is falsified. Yes.
Can I ask something about the previous studies results? I have no idea if CDA has anything to do with it, but there is like a difference between the two tasks in terms of when it's the recognition task, then it's a bilateral task. But when it's the search task, then it's right or left, right? Then it's the lateral task. So do you think that if they were preparing for a lateralized task, they were trying to suppress the lateralized index, but versus when they were preparing for a bilateral task, then they could just still keep that left item there in their mind?
Yeah, so what Sena is referring to is like if, for example, one of these items in the search task overlaps with the location of your memory representation, we know that if you have spatial overlap and also visual overlap, so if they're similar items, then it's detrimental for the memory item. So maybe knowing that there will be overlapping items, people might push the item to long-term memory from working memory. But even though this one doesn't look so, the radius of the search task was much larger. So there was no direct overlap, if that's your logic. But in terms of just being central or not central or bilateral versus not, there we don't have, I think, an option against that. But I'm not sure if expecting a non-lateral versus lateral task should make a difference, in the sense that that same explanation could have hold also in the working memory, like unstudied items. But for unstudied items, we don't see a difference in the CDA. The CDA is equal for both. So it has to be something about being previously studied. Yeah. Still, we can't eliminate your explanation, but I don't think it's super likely, I would say. Yeah. Good question, Joe.
Can I ask something
Yes.
related to that? Could the difference also, I'm wondering, so in the recognition task, or generally the probe, was that from the same category always? So
Yeah.
if you have like a plot, then in the search display or the recognition probe is also a plot, but like a slightly different looking one, or could it be from a different type of category?
Always the same category. So that
Okay,
because
then
yeah, sorry.
yeah. No, then I think my point doesn't make sense, so that's fine. Okay,
Okay.
thank you.
Yeah, thank you too. So the logic was there to ensure that people have a visual representation, that they can't just rely on semantics. Because if it's semantics, the CDA doesn't work that well. All right. So yeah, that's the first experiment. And then we conclude that interacting with the world or guiding behavior doesn't seem to be the reason why we activate memories. Now, the second explanation is protection against interference. And those experiments were run by Senna. So first we look into perceptual interference. The first two phases mirrored those in the first experiment, the previous experiment, where participants learned specific images. In phase 3, each trial began with the presentation of a previously studied memory object. In this case, we had an arrow. So the arrow was pointing towards which of the two items was the memory item. In this case, they had to remember the couch. And then after a retention interval, they had a 2 alternative forced choice task where they chose the correct item using up and down arrow keys. And then we had either no interference before the test or an interference display, a perceptual interference display, items consisting of the same category. And this was blocked, so participants knew if they were going to get no interference or interference. And once again, we measured CDA, the working memory reactivation, anticipatory period before the interference. So we were measuring what people do in anticipation of interference. Here are the behavioral results. The accuracy was again quite high and did not differ between interference and no interference conditions. The reaction time also didn't differ between interference and no interference conditions. So we had no effect of interference on behavior. We couldn't have a strong enough interference, which is a huge weakness, which we will eliminate in a follow-up experiment I will briefly describe. The CDA didn't differ between the two conditions. There was a reliable CDA in both. So people relied on working memory to store the items, but not to a different degree, depending on interference. This indicates that anticipated interference did not affect memory reactivation levels. But as you might notice, since our interference task was not interfering, it could be that it was not strong enough of a manipulation. So we had another experiment. Can you hear me? Because I got an error message saying that my speaker is not detected. People on Zoom.
That's weird because I don't get any messages and I can hear you all the time perfectly.
Okay, perfect. Then never mind.
Sorry for the pop-ups.
That's okay. Yeah, so we had another experiment where this time participants were given a secondary task, not just perceptual information, but something they had to do with, like they were doing a search task and indicating if the target was on the right or left, just like the previous experiment, but they did it before doing the main memory task. There we had strong interference costs, and yet we still didn't find difference in the CDA. Now we can more confidently conclude that the goal of reactivation isn't to protect information against interference. Therefore, whether you rely on working memory or long-term memory isn't affected by how much interference you expect in the world. Yes?
Did you measure the CDA effect before the interference?
Before the interference, exactly. So it's what you do to prepare for interference. After interference, the CDA disappears, I think.
It doesn't usually come back. Usually doesn't.
Yeah, exactly. And it's hard to isolate the roots being due to just something appearing on the screen and messing up with your sensory representations, or an actual disruption in working memory. I think is a bit hard to dissociate from each other. So we usually don't look at what happens after interference.
CDA doesn't last for long, right? It naturally.
True.
Yeah.
Even if you don't have an interference display or a task, usually the CDA disappears after 1 or 2 seconds. So what matters is that what you do in anticipation of that interference for our purposes. All right, so now the third explanation. Flexible adaptation account. Let's examine the effects of anticipating a new task rule. If you're going to switch to a new task rule, you need to adapt to that rule by having the new task relevant representations in your mind. And for that, working memory might be critical. So to test it, we looked into the effects of anticipating a new task rule. Here is the procedure. First, participants were given a task queue, which was either recognition or size. Then they had the location queue that we talked about earlier. It was either the blue side or the yellow side that showed the correct memory item. And in this case, I think it was the seashell. And then after a retention interval, participants were given a probe and they had to indicate if the real life size of the probe item matches the real life size of the memory item. In this case, we had 3 categories where we informed participants that we had the small category, which was about the seashell and cookie size. We had a medium category, which was about the teddy bear, and then we had a large category where it was things like cars and vehicles and things like that. So people know that they had 3 categories. They need to do the comparison. And in this case, a seashell and a cookie are from the same category in terms of the size, real world size. So the correct answer is same. Then on the next trial, they again got a task queue and they got the same memory item that they have seen before. So again, they have to remember the seashell. And at the end, they do another size comparison. In this case, the key is also small, so the correct answer is, again, same. The third repetition, they remember a seashell. The 4th time, they remember a seashell. And the 5th time, they're still remembering a seashell, but now the task changes to something else. Now they have to do a recognition task, where they have to indicate if the probe item here itself is the same or different than the memory item. So even though it's a seashell, it's a different type of seashell, so the correct answer is no. And then they had one last time, so each item was repeated 6 times, so they get the seashell once again, and they do it with a recognition task. In this example, the task changed at the 5th target repetition. So the same target and same task, same target, same task, same target, same task, and once again, but here is the same target, but a different task. But sometimes they got a new task at the first time they see it. So in the previous series, they might be having recognition, 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 and then size when they switch to a new item and a new task. We had the task change at the first time people see this item to see what would happen when people are storing something novel. So it's again a baseline condition, and then they switch to a new task. And here, the 5th time that they see this item, but they get to a new task, allowed us to test the effects of doing something new, a new task rule, while the item has been repeated. So the item should be in long-term memory, but the task rule is new. What happens in that case? And again, we looked at the CDA before the actual task during this retention interval. The accuracy improved with the target repetition. So you can see that it goes from about 90 to about 95% when the same target is repeated. And then when people switch to a new task, we have a task switch cost, and the task switch cost is much larger if the same target has been repeating for a while. So we have the target repetition on the x-axis, and the cost is smaller if it's the first time that they see this target. I'm going to skip the explanation now. If you're interested, we can discuss it in a Q&A. Now it has been about 35 minutes, so I will keep it to the main focus. Here we have the CDA, and the CDA declines as the same target is repeated. This is the same pattern I showed you where I explained what the CDA is. When the same target is repeated, it declines over time. And this is despite performance increasing. Remember from the previous slide that people get better, even though we see less evidence that this item is stored in mind. How could that be? People must be relying on long-term memory. Yes.
But from have you checked for eye movements? Because if they already know what the target is from the first trial, they don't have to rely on the central cue anymore, because they know that the same target will be repeated several times.
Yes, but
So
then
if they are less likely to focus on the center of the screen in the repeating trials, the expected lateralization.
But so we always eliminate trials with eye movements.
Yeah, this was my question.
Yeah, exactly. And then we also have some behavioral evidence, not from this experiment, but where you could see that as the same item is repeated, we don't see the behavioral markers of working memory anymore, which is the automatic attentional guidance to matching colors, for example, that also declines as the same item is repeated, which suggests that even just a few repetitions of the same item is enough to result in a decline in working memory activation levels. Yeah. Thanks. Thank you too. But then remember, we also had new task rules. So if it was the first time that you have seen a target and you switch to a new task rule, it had no impact on your CDA, which makes sense because it's a new item and you have to rely on working memory. But if you have been seeing the same item for a while and the CDA declined, and now you see an increase in the CDA when you switch to a new task rule, which means that a novel task rule triggers the reactivation of task relevant items. So I have been storing something in my mind. I know that I'm going to do something else with it, even though it's the same item I have been holding in my mind. And even though I have transferred it to long-term memory, because I know I'm going to do something else with it, I reactivate it back in working memory. Why could that be? Imagine your goal is to find your favorite chocolate among others. And next, you might shift your goal to decide if it would fit into your mouth. To do this, you might need to focus on different properties of the memory item, or from an object file explanation, you might need to associate the item with a new task rule. In either case, these adjustments might benefit from the neural activity associated with working memory. In other words, working memory could be more flexible to make these adjustments, as opposed to long-term memories that are stored via structural changes that are harder to work with. So to adapt representations to novel task settings, we might need reactivation in working memory. So now we found that reactivation is stronger when switching to a new task rule, which is in line with the flexible adaptation view. I'm going to move on to a different experiment, the last one, switching to a new context, which is task irrelevant. And this was run by Shahjan, who's also here. This was really similar to the previous one, where participants were given memory items that were repeated 6 consecutive trials. This time, it was the background color that changed to a different background color, either at the 5th target repetition or the 1st repetition. So instead of a task rule change, we had a background change, but otherwise it was almost identical. And the task was always a recognition task. So people have to indicate if this matches this one. And again, we looked at the CDA in this retention interval before the task. The accuracy increased once again, similar to the previous experiment. In this case, we didn't have a decline in performance when participants switched to a new context, so new background color. And the CDA was also similar to the previous experiment where it declined across repetitions. When it was a novel item, we had no effect, just like the previous experiment. And if it was a repeated item, we had an increase in the CDA, also like the previous experiment. So they perfectly replicate the previous one. But the main difference here is that what changes is task irrelevant, not relevant. Therefore, these results might be a bit counterintuitive, but let's try to explain why that could be the case. In daily life, performing the same task in different environments often leads to distinct behavior patterns. For instance, when studying, you would typically need to be quieter in a library than a coffee shop. Even though the act of studying is the same, your behavioral pattern changes, which means our brains might be hardwired to reactivate task-relevant information to evaluate the relevance of the item with the new context. That reactivation could be adaptive, allowing adjustments to novel task settings. So even though in this experiment, the context was non-informative, because it usually is informative in daily life, we might have developed habits to look for context changes and reactivate our memory if the context changes. So to go back to the big picture, now we found that a new context also triggers reactivation. So we can confidently put a check mark next to the reactivation account in a new setting. So it is possible that when we adjust to novel settings, be it task-relevant rule changes or task-irrelevant contextual changes, we require stronger reactivation of long-term memories in working memory. To summarize, our findings show that previously acquired long-term memories are reactivated in working memory, particularly in scenarios requiring adaptation to novel settings. We did not find stronger reactivation for protection, and surprisingly, we found weaker reactivation for guiding behavior. These results challenge the traditional view that suggests working memory is the default buffer for retrieved long-term memories, and instead suggest that reactivation levels might be modulated by anticipated task demands. Furthermore, they underscore a key advantage of working memory over long-term memory, which is flexible adaptability it offers. So where do we go from here? There's much more to explore, such as the conditions, other conditions that trigger strong reactivation, the neural mechanisms of selective reactivation, the degree to which the reactivation is under strategic control, and how long-term memory might guide attention without working memory. Because remember, we had less working memory in the attentional guidance condition. So how do we interact with the world while bypassing working memory is a question mark. I would like to thank my lab members and collaborators, two of whom are here. So once again, thank you, Sena and Shahjan, and thank you for listening.